welcome to Winter 2017 Rough Cut series. This is our first Rough Cut, and it's great to have Otto Stein kicking it off. Otto's been at Montana State University since 1990, and he's one of the water faculty in engineering, and so it's really a valuable component to the whole water program at Montana State University. And his research is on wetlands and hydrology and hydraulics, water quality, and erosion mechanisms. And he's been really active in Engineers Without Borders too. So thanks for making the time.
Oh, my pleasure. Thanks for inviting me, both Kathy and everybody in the IOE. I really appreciate the opportunity to come and tell you a little bit about what I've been doing over the years. So as you can see here, I kind of can you guys see that right? It looks. Yeah. Okay.
Yeah.
A little bit of an overview of the research that we've been doing related to wastewater treatment using wetlands specifically. I want to say Otto, Stein, and over a 20-year period, there's been lots and lots of people that I've worked with. I'll try to acknowledge some of the people towards the end on that, so we'll just leave it at that. So a little bit perhaps on my background. I may be not your typical engineer because I didn't get an undergraduate degree in engineering. My undergraduate degree was in something called environmental resource management, and then when I got a degree in soil science related to soil physics, got involved with a erosion project looking at reclaimed strip mine soils and what was the erosion potential on that, which naturally led to looking at an engineering approach to how erosion processes work. Maybe decide I wanted to get a civil engineering degree and focus on erosion and sedimentation. So at one level you could say I was lost and I didn't know where I want to go, but somehow the path through that maze wasn't as random as it might have appeared. So as Kathy said, I got here in 1990. My appointment is roughly 60% teaching, 30% research, and 10% service. Since about 1998 or so, I started really slowly moving out of that erosion and sediment transport field and more into the wetlands field. And I would say at this point, pretty much everything is related to wetlands now. It was kind of a gradual transition over a half a dozen year period or so, but it's pretty much gone that way completely. And also, as Kathy said, I've been the faculty advisor at EWB since 2006. I did step down last year when I was on sabbatical. And I've decided not to step on again, so I really should say that 2006 to 2015. But one of my former students is now the advisor to that, so I'm still involved with it in a fair amount. So that's a little bit about me, a little bit more about treatment wetlands then. So what is a treatment wetland? I guess that's the first question to ask. And essentially what it is, it's a constructed wetland. And again, a constructed wetland would primarily be putting a wetland in where there was not one before. Now, ecologists might argue could that ever be a wetland, but as an engineer, I'm going to say, well, if it's got water and wetland plants and it's got something close to the ecology of that might actually be a wetland. And a treatment wetland, then, the function of that constructed wetland, as opposed to saying it would be for habitat improvement or for mitigation techniques, it's specifically to develop a water quality treatment mechanism. And the water quality that treatment wetlands have been applied to has been everything from mining waste to stormwater. That's something most people take in mind. My focus has been more on domestic wastewater. So really wastewater generated coming in from the sewer system and using a wetland system to actually treat that. Although I would say in general, the approach that we've taken could be applicable to all of those sorts of processes. But when it comes to practical applications, it's been a little bit more on the domestic wastewater side. And again, here's a couple of examples of what different systems might look like, as small as an individual backyard system or in lieu of an on-site system, or for a small community, something like that gets kind of cut off. That's in Minnesota and in Ireland. So why might treatment wetlands be a good way to treat wastewater? Wetlands in general are areas that contain lots of plant and microbial activity. Compared to both terrestrial ecosystems and aquatic ecosystems, I would argue that the biogeochemical transformations in wetlands can be more rapid and more varied than they would in either one of those two ecosystems. In a way, wastewater treatment mimics one of those three. More traditional would be, say, land application of wastewater or using a pond or something like that. So there's aquatic and land. why wouldn't a wetland being sort of an intermediate and having higher biogeochemical transformations, why wouldn't that be better for water quality improvement as well? It's sort of the logic behind that. So we know that wetlands have very large environmental gradients, so large changes in chemical constituents over very small areas, say even just the area within a few millimeters or two around the root, you could have very large environmental gradients. So in wastewater treatment in general, what our traditional engineering approach would be is to string it out like a string of pearls, and we would have one tank that's optimized to do one thing, and it goes to the next one, to the next one, to the next one. Essentially, you compact all of that into one system in a wetland, and you can get all of those things occurring over very small geographic locations, small spatial scales, because you've got these environmental gradients that are really large. So things that would be sequential don't necessarily have to be. So why wetlands research at MSU? Why did I get involved with that? Well, I believe, and I know this is true, they're under-researched and underutilized in the USA. When you talk to the engineering community, the regulatory community, the concept of using a wetland for especially domestic wastewater treatment is almost like, oh, that's novel, that's experimental systems. Yet there's roughly 25,000 treatment wetland systems in the world, and in Europe, they've now become almost a preferred option for small-scale communities. So several hundred to several thousand people, that is the system that they're using. That is the first system they go to, and if for some reason that wouldn't work, they go to the next one. We certainly have not gotten to that level in the US at all. I think they're particularly applicable in Montana because we have the size communities that exactly fit that range that I was just talking about, where we've got sewer hookups with several hundred to several thousand people on the hookup. This would be a great opportunity to take a system which I can tell you does work better. Okay. Why is that not working so much? Well, generally we have a lack of design criteria, really a lack of understanding of what criteria has been developed in other parts of the world. We're not very good at getting that knowledge transfer in places other than just locally. That, of course, then makes both engineers and agencies unwilling to permit these systems. And if it's hard to permit and an engineer is not willing to step out and try to get a permit, then nobody adopts a new technology and we get stuck doing the same thing over and over and over again, even when there is better technology out there that's available. So we need regulatory agencies to accept the technology, and we need to make consulting engineers more aware that the technology works. I think those are the two components to that. And the approach that we took initially was to say, we need a better understanding of the fundamental processes. That leads to better design, better criteria. Now, there's a little bit of a backstory to that. If you want to get research money, you also have to look at fundamental processes. So there's a little bit of all that. Maybe all of this justifies. So here's the broader impacts to trying to get money to go this way. Okay, let's look at some of the fundamental processes. So what has our focus been here at MSU? We have some unique niches here that are available that might not be available in other places. First off, we have very highly seasonally dependent climate. We go from very hot, very dry to very cold and humid and dry climates. So what is the effect of the seasonal variation? What is the effect of plant species selection and the treatment efficacy? From a more fundamental perspective, what are the interactions between the plant roots and microbial activity on those biogeochemical transformations that are happening there? Of course, we can take advantage of sample biofilm engineering when we start looking at what happens at those kinds of at that level. More recently, I've really decided to step back from some of that fundamental work and actually try to look at some of what are the actual in-ground applications of wetland systems. In the last few years, we've actually been able to put in a couple of these systems, including this one that's up at Bridger Bowl. And so we have a pilot system up there, and I'll talk a little bit more about that a little bit later. Coming back to where we started with things, species selection is typically not considered in treatment efficacy. When you look at all of the constructed wetland research in Europe, where they're common, they use one species, Phragmites australis. That would be considered a weed here, so it would be really hard to say that you could put Phragmites in a wetland because it would escape and it would get out. And so there's huge issues with that. The system, the plant species that would get used here, most likely Typha, as we'll show in a minute, typically is not the best species when we actually look at lists of species. It would be very effects on that. So that was something that we said when we look at the literature. In fact, if you look at the design manuals from EPA, they say the type of plant doesn't matter. It specifically says that. Okay, we'll come in a second. We'll challenge that more. Seasonal effects are usually assumed to be equal to temperature effects, and we know temperature affects things like microbial activity. But season, especially when you have a plant in the system, is more than just temperature. The plant responds to season, that changes the biogeochemistry, and hence it probably changes the whole treatment efficacy associated with that wetland. So plants, we know that plants affect, those from the agronomic world know that plants have an effect on microbial processes and redox. We've got things like, nitrogen fixers and all sorts of things associated with that. But that sort of logic has never really been applied to the wetland plants and the wetland ecosystem. So plant season effects on microbially relevant functions are really poorly understood. Okay, and so that was another niche that we felt that we could really move at. We know that plants exude carbon and oxygen. We know that carbon and oxygen are two of the most important drivers on all the microbial processes related to wastewater treatment. So plants must have some sort of influence associated with that. So that was sort of the original focus of some of our original work that we were looking at. So what are some of the factors in a treatment wetland which influence that redox potential, which influences the microbial processes, which drives what the treatment would be of that particular wetland system? Well, the type of wetland. There's many, many different types of configurations. And this vertical flow, horizontal flow, water on the surface, water underground. All of these things have been proposed as different types of treatment wetland systems. How I apply the water makes a difference. And we know that's going to have an influence on the redox. Obviously, if I put more waste per unit area or less, that's going to influence the biogeochemistry as well. So those things are given, and that's where most of the design criteria from Europe has come from, is looking at those factors. Other things that are important then would be the plant species selection in the season. So we chose to focus on some of the things that had not been looked at very closely. How can we assess all of those effects then on treatment performance? And one way to do it is just directly measure the water quality changes that we see in and out. A little bit of a black box approach to that. You get direct evidence of the effect, the water quality was improved, but you really don't get much in the way of what is the cause when you do those sorts of things. So that, of course, is one approach that we did take because you want to demonstrate that they work. The other way to look at this would be to actually look at the microbial populations that are driving that sort of treatment. So we can look at presence and absence of specific functional groups or microbial activity in general. Really what we'd like to get at is activity, but activity is a little bit more challenging to get at. So what we tended to focus on is presence. Are they there or not? As soon as you open up that black box and you look at a wetland now, where do I look for microbial activity? So one of the big questions that we were one of the first, and this is now a common research theme in treatment wetlands, but we were one of the first groups to take that approach. Where do you look in the wetland to be able to look at microbial activity has an important influence? So those are sort of the big pictures that we got started when we started, what do we want to look at when we're looking at treatment wetland efficacy? Oxygen was the thing that we focused on originally. So here's a cross-section of a couple of different plant species. You'll see it looks like a series of straws in there. And wetland roots live in an anaerobic environment, saturated soil. They need aerobic respiration, so most wetland plants are adapted to be able to transfer copious quantities of air, including oxygen, down into the root so that they can fulfill their root respiration. But how much of that actually leaks out? Because how oxygenated the internal structure of the root is makes no difference on the treatment efficacy of the wetland in general. It has to be how much gets out into the environment where the water is. So that's a big, and still is sort of a big unknown on that. Things that we're sure would influence that would be, what's the external oxygen demand? And in wastewater treatment, we measure that by chemical oxygen demand or biological oxygen demand. Essentially, it's a measure of organic carbon. And so the more organic carbon that's on the outside, that's a greater demand, stronger gradient. Stronger gradient should relate to faster efflux of oxygen out of the root and into the environment. So we know that that would probably have an effect. Root and shoot morphology, which would be related to the genera of the species, is probably going to have a difference. And a plant that has a root structure like this might leak more oxygen or less oxygen than a plant that has a structure that looks like this. So species differences could be important. Another factor to consider would be what's the root respiration demand, and that's where season comes into play. In Montana, plants are not actively growing 12 months of the year. When they're not actively growing, their internal oxygen demand for respiration would be lower. If we assume that that oxygen transfer is passive, that might mean there's more oxygen available for processes in winter than in summer. And that was really one of our driving hypotheses that we first got started with things. So, does this influence treatment? So here's a root in, say, wastewater. It doesn't really matter what the species is. That was the best picture I could find. Let's focus on a little more detail on the root in there. So the red line here represents the quantity of oxygen that might be moving down into the root from the above ground shoots. And as this cartoon would demonstrate then, we would assume that most of that would be consumed within the root for the respiration demand of the root. We do know that some of that does leak out, and if there's a wastewater source out here, there's going to be some biofilm surrounding all of those structures in there, including the root. And it's the biofilm that we're really depending on to do the biochemical transformations for the water quality improvement. So oxygen is going to leak out, and some of that should be available to the biofilm. Before any oxygen leaks out into the bulk water, though, it has to go through both the root sink and the biofilm sink. So a lot of the early literature said, well, the water is anaerobic or at least anoxic. There's not a lot of oxygen transfer in there. But what they miss when you just measured what happens in the bulk water is what happens between where the oxygen got to the subsurface and where you're measuring it in there. And there could be an awful lot of oxygen transfer occurring, most of it being consumed in the root, some of it being consumed in the biofilm, driving aerobic processes in the biofilm, even though we don't measure any oxygen out in the bulk water. And so that was one of the thoughts that we had that might explain some of the things that we had been looking at. So how much is available depends on the biofilm processes, and we won't measure anything in the water until we fill both of those sinks. And if I have organic matter in the water, the biofilm is going to be a sink for that oxygen. So our basic approach in a lot of our early work was then to look at, we did lots of different studies depending on who was giving us money. That's really the truth. But there was a general similarity to the approach that we took. We looked at batch incubations, we used synthetic wastewater, we used different contaminants depending on who it was that was interested in what did they want to remove. We did things in the greenhouse, but we used temperature and seasonal variation by varying the temperature and using ambient light in the greenhouse. So we could always have the same wastewater constituents because we were using synthetic wastewater. We didn't have to worry about fluctuations in what's going on, and we could control essentially the environment, at least as far as temperature and light goes, to get a seasonal effect on that. And we made comparisons between species. So I guess give you some idea then of what that might look like. So here's the system that we had in the greenhouse. This is, again, one of the earlier studies. Lots of different plant species in here. Here's what it looks like in May when everything is actively growing. Here's what it looks like in January. This is 24 degrees C. This is 4 degrees C. And so we kind of get this seasonal pattern of senescence and growth that we were able to mimic even though we were in the greenhouse. Here's sort of the results of that original seminal work, if you will, here. So let me walk you through a couple of these things here quickly. 1 year's worth of season from 24 degrees C down to 4 degrees C and then back up to 24 degrees C again. So there's a temperature cycle. In each one of these cycles, we did a 20-day batch incubation, so we actually could measure the data through time within that 20-day period, so we could do things like kinetics modeling of what's going on at the rates. But what we did here is we just picked an arbitrary day, day 6, and to say what was the water quality, and we saw that snapshot in time. And so COD, again, is a measure of organic matter, and this is in the case of removal. So black line represents unplanted control, the blue line is the typha, the green line is one species, Schoenoplectus, and the purple line is Carex in there. And one thing that stands out is that we get pretty decent removal in general, but we see a very obvious temperature effect in the unplanted system without plants. Sort of classical temperature dependency of microbial kinetics is really what we're looking at here. As the temperature goes down, the rate goes down, the temperature goes up, the rate goes up again. And we can see that very well mimics the temperature. We see more or less the same effect with the typha as well, but it's dampened a little bit. Interestingly, with the Schoenoplectus, the bulrush, there is no temperature effect. And the removal is independent of temperature. And it turns out that when you do the statistics on it, it was actually statistically inverted for the Carex, for the sedge. It was actually better performance in the winter than in the summer. Another important point to make, in summer, it didn't make any difference at all. Almost all the data that had come out before that was for warm conditions, whether it be in the field or whether it be in the lab, and you don't see any plant effect. Hence, EPA says plants don't matter. Pretty clearly, plants did matter in the winter. So the next thing is, why would that be different? And I think these two graphs below give us a lot of information on that. If we look at EH, which is a measure of the redox potential, we're down in the negative 200 for both the typha and for the control without plants. That would be the range where we would expect anaerobic processes, microbial processes to be occurring. So year-round, we're anaerobic breakdown, and what I believe we're seeing is breakdown of under anaerobic conditions of temperature effect. But when we look at the Schoenoplectus, and especially with the Carex, we see that the redox is coming up in the plus 200, plus 300 range in the winter, but not in the summer. So in the winter, we have the potential, at least, for aerobic respiration to be occurring. Aerobic respiration should be a higher rate, and hence we're switching the microbial pathways that are removing that organic carbon from an anaerobic process to an aerobic process, which is more efficient and is driving the water quality that's associated with that. That hypothesis is somewhat confirmed when we look at sulfate. It's in the system because sulfate is an alternative electron acceptor to oxygen that can combine with the organic carbon to produce carbon dioxide. And you can see that all the sulfate is used in the two situations that are anaerobic, and sulfate is under anaerobic conditions, sulfate can be used. So we are turning on at least one of the anaerobic pathways in those two systems. And we have them turned on for all of them in the summer, but in the winter, we're not turning on the sulfate removal mechanism at all in the Carex and only slightly in the Schoenoplectus, despite the fact we're getting 100% removal. So if we're not getting any sulfate reduction, we're probably not getting any anaerobic respiration, yet we're still removing the organic carbon. There was no nitrate, so that wasn't a possibility. It pretty much, about the only thing left, and the conclusion that we made from this is that it had to be oxygen. That was in the switching on and off of oxygen that was demonstrating this sort of pattern that we saw in here. And this was nobody had ever done anything like this before in treatment wetland work when we had published this back 13, 14 years ago now when it came out. So this was really kind of groundbreaking work when this came out. Based on that, then again, we looked at a lot of different things. Money from ARCO to look at stormwater, metals removal. So we did similar sorts of studies with that. We looked at organic solvents. This was when Gaines Hall was being redone and the new chemistry building was coming out. There was, I don't know if people were here at that time, there was talk about making it a green building. And the question would be, what do we do for the wastewater treatment for all the laboratories? So we looked at, say, what would happen if we put organic solvents into a wetland. We did some work and published on that. We've also looked a lot more at nitrogen dynamics, a little bit on stormwater. So then there's a period where we start with that basic work, take more or less the same approach. And the underlying mechanisms seem to be consistent, but of course what might be good for domestic wastewater treatment might not be good for metals removal. So I would want anaerobic conditions for metals removal. So I would want sulfate reduction so that I can create hydrogen sulfide, which would then tie up the metals of interest. So good and bad, it depends on what you want to make the application to. but the underlying mechanism is the same in all cases. So this redox and how the plants influence the redox level. We did get another thought to think, well, we picked three species in unplanted controls. How do we determine which plants would be better ones to put into a wetland? So we made the mistake, I gave a talk once and somebody said, the worst thing you can ever do is repeat the same experiment for fear that you wouldn't get the same results. We were stupid enough to try this again. So we picked the same three species and we picked 18 more. We picked 19 species and we did essentially a little bit smaller type of assay, but look, what was the effect of different plant species? And one of our hypotheses on this was that if the plant is an obligate wetland plant, in other words, it's very well adapted to wetland conditions, it would be a plant that would probably be better at sequestering the oxygen within the root for its own respiration and wouldn't leak it as well. And if it was a plant that was only marginally a wetland plant, maybe it leaks more oxygen out, and maybe that's a plant that's better for wastewater treatment. And that was sort of our logic on that. So we looked at obligate wetlands, facultative wetlands, and facultative plants, and the number here represents the decile layer of what are the chances of finding that plant in a wetland. So these plants would only be there half the time, and half the time they'd be terrestrial. These would always be found in a wetland, essentially. So we thought we were going to see some sort of a gradient that would put something like this on the performance. Turned out we didn't. Here is what we found. If you have a favorite plant species, you can look at it. Let's not focus on what plant species is what. Here is a simple numeric ranking on its ability to remove organic carbon. From the best performing species to the worst one. Turns out the worst one was Limus cinereus, but it was only slightly better than unplanted, and unplanted was the worst. So one take-home message is that it doesn't matter what plant it is, it's going to be better. But clearly some plants are better than other plants, and the question would be why. So with a rather arbitrary cutoff at 90% removal of being the top 10 and the bottom 9, again, keep in mind this generic pattern of better to worse. This is averaged over all the temperatures, and we did all the same temperatures that we did before. So this is a seasonal average. Best performing to worst performing. Did not correlate to any plant physiological metric that we could come up with. It just was there. You can see there's some family relationships to that, but really nothing correlated to plant physiology. Oh, wrong way, sorry. Here's an interesting take that we look at that. It's same order, best performing to worst performing, and this is a correlation between that overall seasonal performance and temperature. Negative correlation, positive correlation. So, the better performing plants tended to perform better when the temperature was cold, and the poorer performing plants tended to perform better when the temperature was warm. Now, it only turns out that only 2 of them had significant correlations, but I think if you just put a general ranking, the general trend in that data is pretty clear. The better the performing species, the more likely it was it worked better in winter than in summer, and the poorer performing, the more likely it worked better in summer than in winter. So somehow it seems to be tied to season and perhaps redox. And I would say, wrong way again, it is definitely the redox level. So this again, here's the COD levels in the background. Superimposed on that is how much sulfate is remaining. And again, if sulfate is remaining, that would suggest that it is not an anaerobic process. And if the sulfate is being consumed, that is an anaerobic process occurring. So the better performing species perform better in the winter, and they don't use anaerobic processes. The poor performing species work better in summer, and they do use anaerobic processes. That's sort of a take-home message, if you will, from looking at this. And again, trying to relate that to something about I still couldn't tell you which plant to put in there unless it was one of these 19. I can't tell you why one plant does one thing or another, but that seems to be the linkage between it. It is related somehow to seasonal redox level and how the redox varies by season. So, what kind of practical results can we make of this stuff? We use plants that are adapted to wetland conditions. Don't use that marginally good wetland plant. It's probably not going to grow that well, and that won't make any difference on treatment. use a wetland plant in a wetland. Don't assume most studied equals work best. Both Phragmites, which is the species of preference in Europe, and Typha, the species of preference in North America, were in the bottom 9, not in the top 9 of performance. So there's a whole bunch of novel species out there. There's 10,000 wetland species out there. There's data on what species affect are on 19 of them. So there's quite a few more that may be better. I don't assume that just because that's what people have studied, that's the one you should use. I believe that we should be able to, in concept at least, be able to choose a plant when we want oxidizing conditions and choose a different plant when we want reducing conditions in the system. That could be part of the design criteria that's associated with that. So there's 3 things that maybe we could take advantage of some of that early work. Next obvious approach then is, do these observed patterns, is it due to the microbiology? I've attributed it to that clearly. I've said this is why, but we had no data of the microbiology up until this point. So the next step was then to try to look at the microbiology more closely. So what do we look for when we look at microbiology? Ultimately, what we'd like to know is what's the spatial and temporal patterns of the functional group activity, nitrifiers, denitrifiers, sulfate reducers, methanogens, aerobic heterotrophs, whatever the class of microbes that you're looking for in there, where are they in the wetland and when are they turned on and when are they turned off? That would be activity. Activity is hard to measure by molecular techniques. I mean, we're developing those more and more all the time. Relatively easy to look at presence and absence. So that's really what we've kind of focused on then again. So we could look at, if you will, community structure. What's the percentage of denitrifiers of the total microbial community in there? What is the percentage of nitrifiers and things like that? That's the approach that we more or less take. And then we can compare, no surprise, plant species, seasons, and location in the wetland to be able to say, where do these different microbes live? So here's this column that we talked about in here. And when it was just a black box and all we cared about was water quality in the whole system, we didn't care where in the wetland we were. But now if we're going to start looking for microbial activity, we need to be a lot more concerned about where we live. So we've got gravel, we've got big roots, we've got little roots, we've got detritus, old living roots, dead roots. We've got gravel near the bottom, gravel near the top. Where's the right place to sample? So first cut, we started looking at a lot of these different things. And one of the things that we know, and this is not our work here, but work that was done in New Zealand, this is methylene blue dye that turns blue if there's oxygen available, and that's a plant root in there. So most of the oxygen is leaking out at the tip of the root, not in the back end of the root in there. And so this would happen to be cypress and because you put it in the diethylene, the methylene blue turns blue. You can see that, again, most of the oxygen is occurring near the root tip. So I might have a completely different microbial community at the tip of the root versus somewhere else on the root and on the gravel. And so that was one of the things that we were looking at. So we take our column, we core it, you can see different things that are in there. We take those different habitats and we separate them into the muck, gunk, gravel, roots. We did other sorts of separations too. Those were 3 that became kind of important. And we can do things like DGGE and qPCR. So with DGGE analysis, then each one of these bars might represent at least in theory, a species of microbe. And this happens to be for one plant species, 6 different locations within the wetland, and in winter and in summer. And if you look across, you see some bars that are pretty common. That doesn't seem to make any difference. If you look at this long enough, you'll see bars that seem to be unique to a different habitat or even in some cases to a different season. One of the things that Jennifer Fallwetter, who's a student that was working on this, did a lot of work on was actually try to come up with quantitative measures of what has historically been considered a qualitative measure of what's going on with that. How can we take DGGE gels and come up with statistical quantitative analysis of how much of what is in there. So that was one of the contributions to microbiology that was made from this. We generalize those results then. I think we can confirm that microbial activity drives most treatment processes. If we see a lot of nitrification, we're going to see a higher percentage of nitrifiers. If we have denitrification activity, we have a higher percentage of denitrifiers, etc. But the correlations to the actual water quality tend to be relatively rough when we look at the microbial activity. Probably because we're taking little micro samples within different points in the wetland, and we may not be hitting what is the dominant microbial mechanism in the wetland system. We can say that species selection and seeds influence the treatment efficacy. That was from before, and the results also suggest that that also influences the microbial community structure. So there is a linkage between the microbial community structure and the observed water quality. We can directly measure the community structure. That's something we can do. Trying to measure activity is a little more difficult. What we found is that location in the wetland will be the strongest determination of what's the community structure. The gravel, the root, what type of root, where the root. Season and species also were statistically significant, but usually much less so than the location, which again, maybe in retrospect, is what you would have expected. But structure is only a partial step to linking treatment to microbiology. Whether it's there or not doesn't mean whether it's turned on or not. And most gene analysis wouldn't make a determination if the cell is alive or not, or whether it's actively producing enzymes or not. And those are the issues that we still have to resolve. Everything I've talked about up to now has been talking about the effect of oxygen exudation from the plants. One of the things we really got curious about more recently was plants also exude organic carbon. And that could be an alternative hypothesis for everything that we've observed. Instead of having more oxygen in the winter, maybe it has more carbon in the summer. And so we started to think about that. Could that be something that was important as well? So is our original hypothesis correct, or is the seasonal variation in organic carbon exudation that drives those changes associated with it? It's equally valid. Excuse me. So we consider the denitrification process, taking nitrate to N2O gas through a bunch of intermediates. This is an organic carbon requiring reaction for every one of these steps. These two were highlighted because we actually looked at the genes, the near K, near S for this reaction and for the NOS-Z that would do this, and we also looked at greenhouse gas emissions from this in this particular study. So here the key would be how much organic carbon the plants producing to that. And briefly, here is the same sort of seasonal variation, 24 to 4, back again, adding absolutely no organic carbon to the system. So organic carbon had to be generated internally, adding exactly one stoichiometric equivalent of organic carbon to completely denitrify the amount of nitrate, adding 2 times the stoichiometric equivalent of organic carbon that's in. Now, if we add organic carbon, we should stimulate denitrifiers, and that's pretty clear we did, but we could also stimulate a whole host of other microbes that might take organic carbon. So a 1-to-1, probably all of that carbon isn't going to go to just denitrification. And you can see the general trend is true. You can also see, unlike removing organic carbon, performance is better at warm temperatures than at cold temperatures. But we're only looking at one narrow band of functional groups. We're only looking at denitrifiers. We're not looking at the entire spectrum of heterotrophic microbes that are in there. So we see the temperature effect is a little bit more apparent in this case. The other take-home message with this is there was 2 plant species, Carex and in this case Phragmites, that removed 100% of all the nitrate that we added, regardless of temperature, even when we didn't add any organic carbon. Now that could have been due to plant uptake, removing all of it, but it also could have been due to denitrification. We have some theories on that. In fact, we've parsed this out a bit more, and the answer is both, and it's complicated to figure out what's going on with that. But we can demonstrate that we did the gene analysis, there's near K, near S genes and NOS-Z genes, and even in the system, even though we didn't add it. So they're there. We also looked at the gas measurements at the 2 extremes. So at 4 and 24, we actually measured N2O production, methane production, and CO2 production by essentially capturing the entire headspace above the wetland. And could look at that. Again, real briefly, here is the degradation kinetics of those particular things. So this is the water quality. You can see that it's really rapid early. It it seems to be pretty classic first order kinetics associated with that, whether if I had 0 carbon or 2 carbon load. If we focus on the first 24 hours in this 24-hour period with no carbon in red and with carbon, superimpose a little bit of what we saw for N2O production. So we saw a lot of N2O production in the first day when we had organic carbon added. That's an indication that denitrification was occurring. We didn't see very much at all when we didn't add organic carbon, even though we had huge drops. And we didn't see it very much at the end of that as well. So no, really none for those cases, big changes associated with that. So that would be a suggestion that at least adding organic carbon was actually driving at least one of the components of the denitrification process. It might also just have been that it was inhibiting the second step, and we were producing N2O and not getting all the way to N2O, and we don't have any real way to be able to put that. I could go on this. Let's just kind of move forward a little bit here. What are we doing now, and what are we going to be doing in the future? So we continue to look at some of these process-based studies. So we're still looking at denitrification, analog of roots, looking at biofilm. We're doing a lot more modeling work that would be associated with this. We're also looking at emerging contaminants of concern and what happens with those in wetlands. So personal care products and things of that nature. What happens to those in the wetland system? The thing I want to talk a little bit more about then is we've come to field scale applications in Montana. In this case, in Ennis, Montana, the fish hatchery, we built a field scale system, and we have the pilot system up at Bridger Bowl. We've also looked a little bit at water quality benefits of natural wetlands. And then again, as I said, modeling and outreach. So just real briefly, 3 years ago, we built a pilot system up at Bridger. We have data now for how this works for over a 3-year period. Bridger's happy enough with this, and this is in conjunction with Montana Department of Environmental Quality. In fact, they were a funder on this. We are going to full-scale application, and so all of the wastewater generated at Bridger Bowl will be going to a wetland system based on the study. So that's a success story. We can prove that they work. We also put in a small pilot scale system at the Ennis fish hatchery. This was to remove the solids that were coming out of the fish hatchery. The results of the pilot system were good enough that then again, you can kind of see some of the solids that are accumulating on the surface here. I won't go into the details of that, but then last summer 15 actually, we built the full-scale system in there. So again, Ennis Fish Hatchery won Fish Hatchery of the Year award to the U.S. Fish and Wildlife Service for the wetland system that we built for them. So this is good publicity there too. So we're having, I guess, 2 successes in Montana. We've also then looked a little bit at the Story Mill site, and I know some of you in LRES have worked a little bit at this, but we had some work where we were looking at the water quality associated with a restored wetland. It's just a couple of pictures. Working with one of the consultants here in Down, Respec, did some regrading and work of that nature, came up with restoring the wetland, and we were looking at the water quality effects related to that restoration process. And hence went from what looked like maybe a wet meadow to something that most people would call a wetland. We're continuing to work with DEQ based on the data that we've gotten from Bridger Bowl and work that I'm working with on a task force with IWA to redo world standards for treatment wetlands. We're going to come up with a design criteria for domestic wastewater treatment wetlands in Montana. So we're working on a contract to actually develop the guidelines for Montana. We're going to be putting on some workshops this summer for design engineers so that they know more about how to do things with that. And then the other thing I wanted to talk about briefly is that I am one of the, maybe in what I might call a mistake on my sabbatical last year, I decided to become the chairman of the international conference that's related to wetland systems. So we'll be bringing that WETPOL, which stands for Wetland Systems for Water Pollution Control. There's your website for that. It'll be in Big Sky this August. So we'll have several hundred people coming from around the world. The focus of WETPOL is to have people that work in the natural wetland environment and the treatment wetland environment actually talk to each other so that we can get across information with that, because a lot of work that gets done with natural wetlands obviously has application to treatment wetlands. And with treatment wetlands, you actually have controlled experiments that you would never be able to do in a natural wetland. And so that cross-breeding of information is something that we're really trying to promote in the Wet Pole Conference. And of course, both groups have their own independent conferences. And so this is one where we're trying to bring those people together. So Wet Pole started as really as a symposium in Ghent. You'll see that we've had one every other year since 2005. This is the first time it's left Europe. So one of the options that we're really trying to do here is to try to bring that technology to the US and specifically to Montana. So that's going to take up most of my time this semester. I'm sure of that is getting ready for this. So we've got a nice website. Anybody's interested can look at it. We actually have a call for papers out right now. Right now we're saying to the end of January, but you know how that goes. Different topics that are related to this. It'll be at Big Sky. We've got DQ, College of Engineering, a few companies are now supporters on this. We're still trying to develop additional supporters that would be helping us with that. And we'll have field trips. We'll have obviously a couple keynote speakers and sessions, breakout sessions where everybody can talk about either their new fundamental research or their application and case study type work associated with that. We hope, like I said, to have several hundred people come here to Montana in August for that. So I mentioned, I think those faculty that have worked with me probably know who they are. I think all of us would appreciate that nothing that I showed today would ever get done if we didn't have the students who are actually doing the work. So I wanted to acknowledge at least many of the students. I probably missed a couple that have been working on wetlands work over the almost 20 years now that I've been here working on that. So some of these people have gone on to be successful stories on their own. And a lot of these are master's students. They're actually out in the consulting world now. So they're actually, hopefully they've learned something to bring this up. So with that, thank you for your attention, and I guess if there's questions, I'll be happy to entertain them. Yeah,
I was curious how you approach thinking about the residence time of the water in these systems and those types of controls on the things.
Well, in our case, we were using batch incubation, so the residence time was as long as we put it in there. We have done flow-through systems. I didn't talk about those at all, but this was just batch operations. So we mix up the wastewater recipe, we put it in, and we let it sit there for a period of time, and we sample with time.
Okay.
So the residence time is how long it's in there, or literally the residence time is when we took the sample. The residence time was up to that sample point, and we sampled it 1 hour, 1 day, 3 days, 6 day, 9 day, 12 day, 15 day, and then the original experiments we went to 20 days. We realized by 15 days everything was done anyway, so then from thereafter we cut it off at 15 days. And so, well, we have done flow-through studies. We've also looked at reloading at different residence times. So rather than 20 days, we also looked at what happens if we load it every 9 days, and we load it every 6 days, and we load it every 3 days, so that we sort of reset the system every 3 days instead of every 20 days. There is a feedback mechanism on that, and we published stuff on that too. I mean, I didn't show any of that data, of course. I mean, there's a lot of additional work that didn't have time to talk about. I just tried to cherry pick a few of the key highlights that we talked about and that we found over time. Yeah, so residence time obviously has an effect on what's going on.
Can I follow up then in terms of these full-scale systems? How does water move through the system?
Okay,
in this
so
production system?
the system, both of these systems are now what we call vertical flow systems, so they're unsaturated. So they're pulse loaded. You put a pulse of water on, and in this case on the surface, and then the water trickles through, and then you collect it at the bottom. So how often you pulse it, the volume that you pulse it with, do you recycle? It's becoming a much more engineered system than what you might think of as traditional wetland kind of approach to that. So in a lot of ways, think of it as it's a trickling sand filter with plants. The plants have a very positive effect even in a trickling sand filter. I think that makes a huge difference. And like the solid system there, that was something that was really novel that came out of France about 10 years ago, 15 years ago now, I guess, where raw wastewater, no pre-treatment at all, goes right under the surface. And with the pulse loading and with a resting period, you accumulate the solids on the surface and then you rest it. So rather than anaerobic digestion of the sludge, you do aerobic respiration of the sludge, and you slowly build up a duff layer that essentially becomes peat moss. And what they have found now after 15 years, that performance of that system is actually better than if you didn't let that duff layer come on, because all of the microbiology that's occurring in that duff layer also has an influence on the water quality. So when I first heard that, I mean, I was already somewhat involved in the field. I was like, that's the craziest idea. There's no way that's going to work. It's going to plug up. It's going to stink. It's going to, I was a naysayer. And then I went to France and I looked at that and I go, that's the coolest thing I've ever seen. This is what we should be doing, and it was, visualization is everything. And so one of the nice things about having a couple of systems here in Montana and now having the conference here is that maybe the same realization that I got is what a lot of other people can get when you actually stand there and you actually look at the system and you go, wow, I can see why that works now. You can talk about it and show pictures. There's nothing like standing next to it and seeing it. There was a question there, then here.
Yeah. So Carex was always a good species, all the different Carex species. How much do you think the results have to do with the oxygenation? Simply due to plants parenchyma. Carex has parenchyma, other species don't. Most wetland plants, many wetland plants do. But is there a degree of parenchymicity or something where you just have a direct shunt for oxygen to be entered?
Yeah, another thing I didn't talk about, in partner with some of my colleagues in Europe, we've done a fair amount of pretty sophisticated modeling on some of our data. And our hypothesis of oxygen, while there's some truth to it, it's way more complicated than just that oxygen story that we initially hypothesized. A lot of it might be just simple microbial biomass differences, and maybe Carex, actually, for whatever reason, we don't know the reason yet, but for some reason, it seems to have a higher carrying capacity for biofilm on the root itself as compared to other species. So it's just more microbes in general. So therefore, you're going to have a faster kinetics associated with that. And trying to fit the models that have been developed to our data, the only way we could get fit, we would have had unrealistically high oxygen transfer rates to make it fit if we were varying oxygen. But we varied the biofilm biomass, we could get a better fit to some of that. But like with all modeling, I mean, it didn't. I mean, our data set's pretty comprehensive. I mean, nobody had a data set with all of that data. I mean, we had 4 replicates, we had 3 plant species, we had, multiple temperatures. And the other thing is that we didn't even take any data until 2 or 3 years after those plants were pretty mature. And when you look at the general literature on this, everybody wants to do their 1-year study. So they grow some plants, they let them grow for 3 months, you take some data. That's not even a mature system yet, and we really waited till the system got really mature. And so I can say that the data set that we've developed is probably the most modeled data set there ever was, because not only work that we've done, I mean, at this point, it's 20-year-old data now. Anybody that wants it can have it. Lots of people have used it to try to calibrate some of the models for what's going on in wetland systems. Question?
So have you looked at combinations of species, or have other people in Europe on the application side looked at if there's any more benefit to
Yes and no.
species versus multiple?
Yeah, there's a group out of University of Montreal that's done some work with, obviously it's something that's not a monoculture of one particular species. In Europe, everybody plants Phragmites. Phragmites is such a aggressive species that it tends to be pretty much Phragmites forever if that's what you plant it. And you do get, I've seen it, you do get some weeds that are growing in there. Nettles seems to like to come in, so you get nettles as well as that. And up at Bridger, I don't know if you noticed, there's kind of a checkerboard in there. We actually planted 2 different plant species. We put bulrush in 2 quadrants and Carex in the other quadrant, and we have the ability to sample underneath those 2 things. What we found, at least at Bridger, is that the bulrush hasn't established very well. I think it's not so much because the plant doesn't grow there, but there's some sort of rodent that likes bulrush. Pretty heavily. And the Carex has done much better, so we've actually planted Carex in between the bulrush so that we can get plants over the whole thing to occur. Ironically, this last year, the bulrush grew really well. So you never know about some of these things. But yeah, there's been some work that's been done on looking at thing, other than a monoculture. Yeah. There was, yeah, okay.
So it seems like an interesting question with the issue of deploying this in Montana is that in a lot of our small communities, there's at least a competing model of a privately funded water and sewer structure, right, which has been really problematic. But I'm wondering about this question of like whether or not the private aspect of this creates opportunities for innovation and deployment, or is this so cheap and efficient that private industries don't have a good incentive to get into it?
I think there's a lot of commercialization potential of this technology. Certainly in Europe, that's been done a lot, and there's quite a few consulting firms that they're wetland experts in that. And I know I was in Europe last year for my sabbatical, and there's a couple companies that are really interested in developing an American branch, of course, and coming over here. If we can get DEQ on board and we can consulting engineers on board, it wouldn't necessarily have to be a private entity. But of course, if I can convince a private water and sewer district that this is the way to go, that could be a pretty direct mechanism to go to direct application with that. So I don't think it's necessarily tied to privatization, but you're right, that could be a
Sort
less
of a contextual factor. Right?
yeah, there could be definitely an easier way to maybe get some of that going if you, and if somebody here in Gallatin County, somebody mentioned, I can't remember the woman's name, who's doing a lot who's doing a lot of work on that. Figured I needed to have a conversation with her somewhere. Yeah.
I was just wondering if any of the wetland plants that used in these studies might have any potential as a biofuel stock.
That was one of the things we talked about originally. Some of our original money came from USDA, and so looking at it as a food source or as a biofuel potential, I would say the answer is yes. The issue is harvesting. So is it worth harvesting to do all of that? And there's another group in Europe that has done an awful lot of work at looking at plant uptake. And if you talk to the general audience, most people think, oh, nutrients are removed because you have plants and the plants remove the nutrients. But, as you know, the plants reach some sort of steady state carrying capacity on that. And you look at long-term nutrient removal by plant uptake, especially in a free water surface wetland where anything that dies falls back into the water, it's kind of neutral. And there's a seasonal effect in plant uptake of nutrients, but it doesn't necessarily go on an annual cycle. Whereas subsurface flow system, like what we're talking about, if the above ground plant biomass is either harvested or blows away with the wind, there might be a little bit of nutrient removal mechanism that way. But the dominant removal mechanism is microbially driven. It's the same thing that would happen in any water quality sort of approach. You got nitrifiers, denitrifiers, whatever your source is. Phosphorus removal is a challenge because there's no real biological phosphorus removal mechanism. So wetlands are not very good at phosphorus removal, but they're really good at removing organic carbon. They're not bad at removing. We now have systems that can really 100% nitrify, but then they're not that good at denitrification. We have systems that can denitrify, but they're obviously not good at nitrification. And then there's some systems that are sort of, if you can get it to nitrify, it'll denitrify whatever it did, but it may not nitrify that well. And I could go on and on. I mean, there's different, that's where the hydraulic operation and the type of wetland comes into play about how to do that. And up at Bridger, then we've got two systems. We've got the first stage, which is primarily remove organic carbon, and then it goes to a second stage, which is aerobic to nitrify, and then we recycle the nitrate back, try to mix it with the raw organic carbon that's coming in, and we have an anaerobic and an aerobic zone in the first stage, so that, and the key is to get the balance between the aerobic and anaerobic processes right, so that the nitrate that comes in can then be used to remove the organic carbon without having any organic carbon bleed through to the second stage, because that would ruin the nitrification step. And again, it becomes, engineering process type research at that point. You just start making your best guess as to what's the flow rate and what's the right mode of operation, and you start trying it and you get the water quality, and then you go make an adjustment from there, and you move on again. And it's an optimization technique. There's still plenty of work to be done in that. But I think the basic concept is down pretty well. But coming back to your original question, yes, you could use it potentially with that, but the cost of harvesting may not be cost effective.
I just want to let all of you know, Kathy had to leave, so I told her I would wrap up, but it's a little after 1. And so I just want to say thank you so much for coming. This is great.
My pleasure,
Actually, a
yeah.
really nice way to kick off our rough cut seminar, which is designed to be interdisciplinary across campus. So thank you so much. And a couple announcements before you guys leave. I just want to make sure Finn Poulter is going to be on campus next week, and he's going to be giving a rough cut, but it's going to be Tuesday at 10 a.m. It'll be in the same room, but hopefully some or all of you can attend that. And then on Wednesday, we'll have a regular rough cut Wednesday at noon, like we always do. Carl Yeoman will be giving his talk in this room. So we kind of have back-to-back days next week. Really different topics, both really engaging and interesting, so hopefully you can make some of those. That's it for announcements, but thanks, and thanks again, Otto, that was great.
Look.